This one's kind of unusual. This time, instead of disks or shells that we could add up to find a volume, now we're doing something known as cross sections. If you look at these ideas, what they've done is they've taken a basic geometric shape. And it's amazing how you can actually look in architecture, in different solids, in designs of different things. When you want a solid 3D volume, a solid 3D shape, how often, it seems weird, but how often you actually just see a basic shape used again, because you wouldn't recognize this, you wouldn't think of this as circles if you saw it nice and smooth. Triangles, likewise, rectangles or squares, rectangles. All we're doing is we're taking that shape and stacking them one right next to each other to make an interesting little volume. Once again, you see a whole bunch of very thin objects. The thickness of each one of these objects is dx. We're going to use an integral to add them all up, but what are those? Well, actually, there are a whole bunch of triangles put together to create this shape. And really, when you take a look at it, you're like, oh yeah, they really are just triangles. These are equilateral triangles. So what it helps to do is, you need to know some of the geometry behind all this. You need to remember some of your formulas for basic geometric shapes. So the cross-sections method adds up these rectangles, squares, triangles, semicircles, whatever it is, and adds a little thickness to them so that you see it's not just the area of a triangle, but it's the area of the triangle times dx, the thickness of each one of those tiny little triangles. The area of the triangle times dx. That makes it a 3D shape, and it gives you a volume. Here's all your volumes over here. Squares are pretty obvious. You just need to know the base of the square. Triangles, these are a little different from base times height over 2. But these are what happen when you have an equilateral triangle. All three sides are the same, and we only know what the shape of the base is. So how do you get a formula for the area of one of these triangles if you only know the base? Same thing, a right isosceles if the leg is the base, or a right isosceles if the hypotenuse is. A semicircle if the base equals the diameter. Remember, a semicircle has cut the circles in half. So it is pi r squared divided by 2, but you have to remember the base of this object really represents the whole diameter. You see it's the diameter of the shape. So let me tell you about the base of this. So remember, this is going to be a 3D shape. You need the base. That's this area. It could be any area. It could be a circle. It could be between two functions. But you need to have a base, and then you need to have something coming out on the z-axis, something three-dimensional. For example, if we were using the triangles, we would have equilateral triangles that would be coming out of the board like this. If we had a rectangle, let's just say the base of the rectangle and the height's always double the base. And you would just take that, and it would be coming straight out of the board like that. Semicircles, same thing. You got a semicircle, it comes straight out of the board. And how do we know how tall it is? Here's how you can do it. You take a tiny little rectangle out of the middle there. You're going to say the base. Remember all these formulas over here? They all have a base, just like most geometric formulas do. And the base just happens to be b, and the thickness just happens to be dx, and then you just need to use your formulas from there. Now, the whole trick in doing this is you need to be able to find the length of that base, and it's the same thing as the radiuses we were looking at before, or heights or lengths or whatever. If you want the length of this, you take the top function minus the bottom function. If you want the length of something that goes up and down, you take the top minus the bottom. That'll give you the base. If you're trying to find the volume of each of these shapes of either a square, an equilateral triangle, or a semicircle, you just need to remember your formulas here. A square is going to be the base squared times the thickness. An equilateral triangle, as you can see over here, square root of 3 over 4 times b, would be the square root of 3 over 4 times the base squared. And a semicircle, likewise, just like this formula here, looks just like this one.